And I think we are in good shape to have about 20 minutes of panel discussion. And so we'd like to invite the 4 speakers up to the stage here. And I think we'll open it up first just to you all and see if anyone in the audience has questions for any of them or all of them or.
Turn this off.
Yeah.
Oh yeah.
Oh yeah, you got the worst seat.
Oh yeah.
Plug it.
Oh yeah. Wow. Yeah, cool. Much better.
Okay. Wait.
Well, the real dream is someone hits the
Yeah.
Background.
Actually, I have a question. Is right now a lot of climate tech it's have a same challenging is scaling up. So it's meaning for you. It's can you give us a little detail about how the AI applying for the scaling up in terms of such as product design and also manufacturing?
Yeah, it's a great question. So I would say that, I mean, I'm not like an expert in every single area that I talked about, just as a bit of a caveat here. But what I would say is that when it comes to designs, I think actually Jinhua's talk was really good at talking about this idea that there's places where AI can really help you be creative, right? Where you maybe uncover options that you didn't see before. And that's, I think, a really good use case. That's also where this example I gave of using AI for accelerated battery design came up. And similarly, people are using that same paradigm of, analyze past experiments, suggest future ones by basically extrapolating from that data. A human might extrapolate from that data in one way, a kind of algorithm might extrapolate from the data, and now you have many different options on how you design a battery that are maybe more diverse than the set of options you would have come up with before. So I think that general kind of paradigm of kind of providing more recommendations or more creativity that allow us to act on something can be really helpful. What I would say though is that when it comes to the difficulty of a lot of climate tech startups scaling up, sometimes it's the tech, but sometimes I think it's the business models. So there are lots of things that are fundamentally good for the climate that are aligned with dollars, but there are many things that are not currently monetized. So for example, right now when you think about, and Sara can probably say much more about this, when you think about forests and ecosystem services, there are ways to monetize kind of carbon in that context, but the value that an ecosystem provides to you is so much more than its ability to sequester carbon. And so what's the business model behind that? Behind actually scaling a company around that? Or some of the horizons of change here are quite long. So for example, I think there are many places on the electric power sector where if you create huge efficiencies, you're changing a global system where many people are buying power, that you can make a lot of money from that. But because there are lots of regulatory barriers or operational barriers in terms of just changing how people who currently run the system or regulate the system actually view it, then the timescales you're dealing with are much larger, and investors often get scared by that. So I think some of it is tech can help with the product innovation, but I think there's a big part of just making sure that you have kind of business models and investment dollars that are cognizant of the kinds of risks that these applications can face and sort of are willing to take those kinds of risks in order to kind of deal with the longer horizons, for example.
Yeah, thank you very much. I have a question to Sara. What exactly are you doing on the design of neural networks in order to cope with auto-distribution prediction errors?
That is a great question. I think actually, so most recently, I've been, the research direction I've been taking here has been more of a, how do we understand good selective prediction, and how do we kind of probe existing sort of methods for out-of-distribution detection than actually architectural, specifically just changing architectures of neural networks. Mostly just because I see that as a much more straightforward path to impact. I honestly, I mean, as someone who does, and who has in the past and does still work methodologically, sort of in the standard AI or computer vision methodology space where you're changing loss functions or changing the structure of a network. there's a reason that data-centric AI is growing so much in terms of like its relevance here, and it's because almost never does an algorithmic change come anywhere close to just doing a better job with your data, either getting cleaner data, scaling up the data you have access to, or thinking about ways to like help experts, particularly in these spaces where like I can't just go to Mechanical Turk and be like, hey, what is this, an American crow or a European raven? Like they don't know. So the expertise is so expensive. Finding ways to make an expert really efficient at like scaling up data processing ends up being more impactful than changing a loss function or changing like the structure of an architecture. I think both are good. We're losing biodiversity so fast that I'm often making choices in research prioritization based on faster paths to actually the answers we need, as opposed to like building hammers and looking for nails.
So the second question that I also have. So I saw that you could significantly improve your data efficiency with active learning. And I was wondering whether you also could see improvements in the auto distribution performance.
Yeah, exactly. So one of the things I think is really interesting is this question of, as the system that we are monitoring is changing, like how do we make sure that our machine learning models aren't explicitly hurting our ability to recognize that change? And this is kind of that exacerbation of like the intersection between things being rare or being out of distribution, or kind of like, how do I want to say this? You can have a really common species, but at the edges of its range margin, sort of the edges of like where habitat is suitable for that species, it will be rare. So it's not necessarily always here like, is this species just rare overall versus like, is it rare in this context? And so there, out of distribution detection gets kind of complicated. Like what we want to detect is when things occur in places or in times we don't expect them to, because that actually means we're seeing like range shift. We're actually seeing the margins of these range change. And so there's then, because you might in some cases have access to a lot of data for that species just in different contexts, there's maybe different mechanisms to think about out of distribution detection that's not just like, have I never seen this thing before, but have I never seen it here before? Does that make sense? But yeah, we do actually, I think there's, one of the things we've been doing a lot is thinking about how do we build, ecologists often want to know how the population of a species is changing. So not just where is it, but how many are there, and is its population in decline or is it growing? The most robust mechanisms we have to do that are sort of these classical statistical mark recapture methods where we need to be able to know if we've seen this individual before. So there's a bunch of biometrically marked species like zebras and giraffes and even sort of things that have contours that are recognizable like elephants or whales, where we do have systems that can be, to some extent, pretty robust at recognizing individuals. And this is sort of an active area of growth, because you can imagine that individual ID is the most long-tailed problem and is fundamentally always open set, because always new animals are being born. And so what we're looking at is, say you get a whole new population of elephants. You just moved to a new country, and now they want to use a system to recognize how many elephants are there. Can we essentially build these graphs of like estimated social networks of those elephants based on where and when they were sighted? And then on top of that graph, really, really efficiently ask an expert, are these two the same? Basically, is this edge like the same or different? To be able to then really quickly get a clustering of the number of actual individuals that count over that area without needing to actually go in and teach someone to ID 10,000 different elephants, because that's a really hard problem.
Although you now have 30 people who can ID the American crow in this room. I want to make sure that we open it up. I want to make sure that if other panelists have comments that you guys weigh in as well on the same question or ask each other questions. And also see if there are others from the audience. Yeah, over here. And then over there.
Thanks a lot. My name is Ernie. I'm a PhD student in the Civil Environmental Department. My research is related to vegetation drag and flow, so modeling flow as well as using images to find what are the densities of vegetation, so quite related to the talk today. I'm just curious from your experiences, because a lot of these machine learning algorithms are treated as black box and hard to interpret. So from your experience, how important it is to have a feature that is explainable in terms of like ocean modeling of flows, or even features you extracted like edges of an elephant or color. Like how important it is that the machine learning is able to deliver a explainable feature so that it's convincible or usable by people. Thank you.
I think it probably really depends on application. My motivation is always physical understanding, so I would always want to understand what's happening. And I feel like neural networks sometimes are not explainable enough, and then perhaps maybe something like equation discovery or something that you can actually look at and understand the different components of what you're learning might be a better method if you're really interested to get down to the kind of physical essence of it. But if your application is detection, I mean, maybe some are more important than other. I mean, I don't know the answer to that, but from my perspective, I always want to know.
I also think we have like hundreds of years of like biology and chemistry, these life sciences, where we have built good, robust experimental practices to try to probe systems to understand how they work, even if we don't necessarily have ground truth. I think in the machine learning community, we should really be influenced by that and actually think about, yes, we can't build theoretical guarantees of what's going on inside this system, but we could think about depicting hypotheses and then probing those hypotheses in statistically robust ways to try to get the best possible sense of what the factors are.
Or building in constraints, like physical constraints.
Yeah, exactly.
That is a way for you to direct your model into the direction that you know is more physically robust.
Do you ever have to think about explaining why to people?
Indeed, that's a great question. I mean, so first of all, let me talk about one of the extreme views, right, which is saying human understanding is overrated, right? So we have this 3 pound of a brain, something we couldn't understand. I mean, there may be entire different intelligence that is beyond our understanding. That's extreme view on that. We should put it there. There's some possibility that's true, right? But here, I'll come back to the more practical one. In machine learning, we have mostly the high-dimensional data, right? But human brain, by its nature, can only handle a low-dimensional. We can handle maybe 10 variables at the same time, right? If you give 200 variables, nobody can really make sense of it, right? That's kind of the challenge here, right? But there's several things you can do. One is, as the feature one, you can at least let machine learning tell you which variable is more important than the others, right? Make sure you don't miss it in your human engineered model, for example. That's a very basic level of things, right? Then the other thing is people try to interpret the cell level of the neural network. Probably that's hopeless. But you may explain at the layer level. You may explain at the attention level, some visualization. That's another possibility people try, right? The other thing is also what do we mean by human understanding? That's itself is very ill-defined, right? Often one way to think about it is if you can kind of simulate in your own brain the process, you understand it, right? That's one version of it. Can we simulate whatever the machine is doing? Probably very difficult on this, right? So often we do, we human beings, we often decompose, often in the linear way. We say this whole problem has 5 steps. Step 1, this, step 2, this. When you put the linear way, we kind of understand it, right? But linear construct clearly is a very small subset of the possible construct in it. So sometimes we may say that we force a linear structure for the sake of interpretation at the price of predictability. In certain cases, that may be a price worth paying, right? Lastly, I would just say that, so for many of us, we're scientists, this interpretation is the goal here, right? If you're an engineer saying, I just want to solve the problem, sometimes you have a lesser criteria. But as a planner, for example, we have even higher criteria. Explanation just not a curiosity matter. That's the job, actually. If you cannot explain your model, however good, it doesn't matter on this. So I would say the different degrees of importance in that as well.
So we've heard about the kind of resolution you need for good ocean modeling. What kind of resolution do you need for climate modeling? Do you have to model butterflies in China to predict typhoons, or I know there's not a system big enough to support that, but is there a sweet spot?
Climate in terms of weather, long-term.
Like WRF or something?
Yeah. That's a good question, because for the weather, it depends on the time scale that you're interested in. So synoptic time scales like 5-day, 7-day, then you go into much higher resolution like single meters, but that's a regional model. And then in terms of the global, it's usually 10 to 100 kilometers in the atmosphere as well, but you have such a much larger range. The atmosphere is also slightly easier problem in terms of you have a lot more observations to constrain, like you have satellite imagery and you've got decades of actual in situ measurements, which the ocean you don't have as much. And there's a lot more interest in terms of application in terms of storms and flooding events and heat waves and stuff like that. So you tend to have more data and more models in that sense. But the resolution is slightly higher than the atmosphere, but the timescales are much faster because hours matter.
Hi, I have two questions. One for Professor Jinhua Zhao. You said that humans are not that good at imagining or perceiving multidimensional data. What are some good examples of using ML to represent the city, like multi-view cities? I think that's what you mentioned. And the second question is for Professor Sara. I think in one of the projects you shared, you simulated tree growth, and you said that they're rooted in environmental conditions. What are some examples of these conditions that you can specify for the model?
I mean, I can answer first because mine's pretty straightforward. With our current very preliminary models, it's literally like temperature and rainfall. That's it. Oh, and elevation. So we had like 3 parameters that were sort of built into this mechanistic model. No. Like it's an input. And then, oh, you mean like you could show the growth over time? I mean, I think the way it currently would be, you'd have to like set some stuff, grow it for a while, change the stuff, grow it for a while. But like the input is like a tree model and some conditions. Super preliminary work, let's be clear. I also think that particularly for stuff like this, we're now really scaling up our evaluation of it and more from a calibration perspective. I think there's a lot of potential for this like sort of merged like future modeling at the order of like individual trees plus like all of the other information we know about cities, about air quality, about all this other stuff. But I think that's definitely future work. Go ahead.
Sure, yeah. The two part of the question, one is this high dimensionality, right? Like take a typical transportation system like Boston, you may have, say, 5,000 road links, right? Each of them has its own, say, observation. You can track the speed, the volume every 5 minutes, for example. So you have a 5 minutes precision of 5,000 variables moving along for like 10 years, for example, right? The 5,000 link, they will be partially correlated in terms of the speed, volume, et cetera, right? That pattern of complexity, I don't think human brain can appreciate, right? We just don't know how to think of 5,000 variables at the same time, how they correlate to each other, right? That's one thing. But the second thing, you talk about the multi-channel view of city, that's a distinct but important point. If you ask at MIT who studies cities, right? So I'm from urban planning, I'll say, oh, we study cities, right? But civil engineers study cities, right? The economists study cities, sociologists study cities, I mean, political science. You'll find that all the disciplines, they all claim that we study cities, right? But is MIT's city study interdisciplinary? I will argue no. We all use the word, but for example, one way to look at is this genuinely interdisciplinary is to look at what type of language you use to communicate with each other, right? So for example, if I'm an urban designer, my language of communication is graphs, these drawings, right? Aesthetic appreciation there, right? But if an urban economist, you use urban like economic models, right? Transportation will use the networks. You'll find that all the disciplines not genuinely interdisciplinary, we really use entirely different language to describe it. So there's no foundation even to really meaningfully communicate, right? One thing the machine learning could possibly do is put all the different modes of communication in a unified format, right? So if you were to predict the number of cars people own, previously you put socioeconomics, income, et cetera. But now you can put the satellite image of that neighborhood in there. You can put some people wrote a history about car ownership in Boston as a historical language into the model. You can put graphs into the model. So now, at least machine learning give a potential uniform foundation to digest all the information in it. So that's a kind of a prospect for better communication among different.
I think we have time for one last question. David had his hand up.
Thank you. Hi, everybody. I'll keep it quick. My question is about tech transfer. I'm curious if you can speak to some of the pathways that you would like to see your work kind of deployed in the real world.
I have a lot of my work deployed in the real world, and I would say it takes a lot more time and effort than writing the papers, and it's a lot more important. But that's like my own opinion, and everyone has different opinions. I think, at least in my space, in this space of sort of environmental monitoring, biodiversity monitoring, the biggest challenges for tech transfer are technical capacity on the side of the users. So there's kind of two historic approaches there. People either think about like, okay, we've built this whole system, this whole model. Our users don't have a lot of technical capacity. So what we need to do now is we need to wrap all of this in this very complicated GUI where it's like no code for them. They just have to learn to click things. Like there's still a learning curve, but we're not making them do any code. More and more, I just think that in these spaces where we don't have a lot of resources, that is not sustainable. So I've really started investing much more into mechanisms to teach technical capacity to users so that they can actually operate with like lightweight sort of GitHub repository style code instead of actually needing to build and then somehow fund the maintenance of some sort of very complicated like GUI that needs to operate on everyone's different desktop system and all these different things. But I think that's very different if you have a sector that has a lot of funding or there is a clear path for sustained maintenance of a tool where it might be used.
Yeah, I would say in the power sector and some of these kind of, for lack of a better word, like sort of old engineering sectors, I think cultural shift is actually a big aspect. And so I think often when one thinks of tech transfer, they think about you sort of develop a technology in the loop with a stakeholder, and that's the actual technology that gets deployed. But sometimes there's an aspect of your work might be trying to demonstrate that a particular kind of thing is possible, even if you're not necessarily doing it in the most realistic way, in order to enable that conversation to happen about then what is the more realistic way to do it and what is the kind of infrastructure that needs to exist to allow us to get more realistic about it. So for example, in the power system, you do need access to better simulation environments, more granular data, and ways to really both develop methods that are actually contending with the sort of real nuances of what's going on in the system, and also kind of pathways to mature those methods with more and more kind of like challenging scenarios that you actually face on the system, ways to validate them. But nobody's investing in creating that infrastructure until you sort of convince them that there is a pathway that infrastructure would be useful. So yeah, so I think cultural shift is I think a lot of what I contend with in my work, with the view towards that cultural shift leading towards the kinds of like progression pathways and simulators and stuff that you would sort of envision as the infrastructure for then the transfer of the actual tech.
Any other last
maybe
thoughts
I'll
on
add
that?
the Chicago example I give. That's really a great question there, right? The only reason it gets implemented is not like we have a better RL model there. It's because we have the institutional support from the president to the supervisor all the way to the drivers there. That's really the key there, right? Give an example why often the technology change to work, you have to come with it an institutional redesign, a process redesign. I'll give you one specific example. The IO suggested the bus driver would say, hold the bus for 2 minutes before it dispatch, right? When we talked to the driver actually told us, I cannot do that because my current incentive structure is such, if I deviate from the schedule, I get penalized. The customer get a better waiting time. Sorry, that's not my business. My salary get cut if I do the right thing, right? So therefore, all the IO technology only work because we have to also change the incentive structure, the business flow in order for it to work. So that's what the really key difficulty of a tech transfer is.
I also think an important point here is that like it's not the same for every application, clearly. Yeah. And a huge part of what makes tech transfer possible is really like investing the time and the resources on the side of the researchers to directly engage with the end users, make sure you're sort of building something that someone's actually asked for or there's sort of a clear need or convincing them that there's a need. Yeah. And I think without that like pretty heavy investment in interdisciplinarity and the deployment of the technology, it just won't happen. And we see so many papers in this space, right, that are like, this is gonna change the world, but then they write the paper and the incentive structure at that point kind of ends on the academic research side, right? Like we're not really incentivized, talking about incentive structures, to deploy stuff. So it takes personal passion, and it also takes away from writing more papers. I think that's another thing that needs to change in the way we think about academia if we want to be impactful.
I feel like I'm probably the least practical of the bunch, but I think the intersection of kind of where my work interacts with technology might be geoengineering, and like how that would impact people, for example, that live along the coast and might be more influenced by like sea level rise, for example, which is like an ocean climate change impact. And I know that there's starting to be, it's very new still, but like more tech companies that are working on climate predictions and how you might geoengineer the environment to be able to adapt to changes that you would see from climate models. But I'm personally not there yet, but I'm super interested to get involved if you have suggestions.
Well, and with that, I think we're out of time, but I mean, this has been, I think we could go on for another hour easily here. Fantastic presentations and fantastic discussions. Let's thank our panelists and speakers again. Super grateful to you all for taking the time, and thanks to all of you for coming and the great questions, and enjoy the rest of your day. Thank you.